What was the table? Yes, for fine. Integration is not a problem. I was telling something. Yeah. Alright, it comes. So, once you integrate this equation, left hand side, which is just velocity of function of velocity, right hand side just function of r, and you put the boundary condition this. VC square. That I given in the assignment, just one line integration. You put that integration constant vanishes, transonic solutions, you get the final equation as like this side directly. Let's call this VC. Let's call the integration constant K. Okay. Left hand side is function of velocity, right hand side is function of r, perfectly integrable. Put the boundary condition, this is the solution. Okay, this is what I gave in the whole exercise I gave in the assignment, but I have 90% solved it for you. Now the physics come into picture. Once I put the boundary condition, why do you need the constant of integration? So what you need to do is, now velocity is a function of r, right? Velocity is a function of r. Now we look at the physical meaning of this. Just plot this. It's not just v is a function of r right away in the algebraic equation, but you can still solve this. Bisection. From bisection you can solve it. If you solve it, what you get? I want you to solve and check it, okay? Because it's very insightful. Now we come into physics. V has the two types of velocities. From the start, matter is going out, positive speeds, matter is falling in, which is basically falling into the star. So you give different boundary conditions. From the surface, if you give the boundary condition, if you give this boundary condition, R equals RC, if R equals to RC, V equals to VC. If you give this boundary condition, you will see when you solve it, you don't need to give other boundary condition. What is the speed of the matter at infinity or what is at this surface? There's a unique solution for that. At V equals to, let's say this is VC or sound speed V. Okay. At R equals RC, this point, you will see that solution comes like this. And you can see it. At R equals infinity, velocity becomes constant. Constant means it probably it keeps on increasing, becomes constant later on. That's only point. So this is the typical solution of Wick's. Another solution is, there are two solutions in this one. One is, what this signifies that if the So this is an outflow solution. The matter is going out. It's an inflow solution. Because at infinity, and the matter is falling inside, it has no speed. It goes to zero. Right? I mean very slowly, because at infinity there is no gravity. When it comes closer, its speed increases because of gravitational acceleration. At some point it crosses the sound speed, called critical point.
Absolute value of velocity. Talking about an inflow solution, the velocity should be negative. Okay, sure. So
for plus v and minus v, you get two solutions that you will solve in the assignments. Okay, so this is spherical accretion. And this is spherical winds. Now there are many things here which are insightful. At the sonic point, if you solve this equation numerically, suppose you do not have analytic solutions, you solve it numerically. Because if there are complicated terms, if there is no isothermal condition, adiabatic, once you take the adiabatic case, you cannot obtain this kind of solution. Then you have to solve this equation using some numerical method, let's say Runge-Kutta or Simpson's or whatever. In that case, you can integrate this numerically, but you will encounter a problem. If you solve it numerically, you will not be able to solve. Why? Because what happens at V equals C? Something peculiar happens. At V equals C. At V equals C means sonic point. What is dVdr? Let's write it again. 2c square over r minus gm over r square divided by e square 1 minus c square over v square. Okay. If you put v equals c, the denominator is 0. This is 0. But we have seen that numerator is also 0. Because left hand side is 0, right hand side is also 0. So dVdr is basically 0 by 0. If you solve it numerically, you encounter this problem. When dVdr becomes 0 by 0, you cannot find out the slope. If you start solving from here, you can reach here, but you cannot find a solution here. It's a very big problem in numerical astronomy. For transonic flows, it's a problem. Does anybody know how to solve this? L'Hopital's rule. You use L'Hopital's rule. So if numerator over denominator. I can remove this part, right? You cannot see anything. Great.
It's
L'Hopital's rule. So L'Hopital's rule says, let me write here. dVdr. I can design a numerical problem for that as well. We can do this. So dVdr at r equals to rc equals n prime over d prime, which is derivative of numerator and denominator. Even numerator and denominator both are 0 at some point. The derivatives will not be 0. So 99% problems you will not find it. If derivative is also 0, then you go to second derivative. We very frequently encounter these problems when we solve the equations numerically, because this is just an ideal world. So once you find derivatives, you can find the slope here. So this is the slope, and then you can solve the equation numerically. This is L'Hopital's rule. Okay. Now we come back to the example of storm. For a storm, now what is the difference between solid objects and fluids? You take a solid object, So with 11.2 meters per second speed, it will go to infinity. It will never come back. But this does not necessarily apply in all cases on fluids. For fluids, escape has a different meaning. You have to throw it with certain speed that it crosses the sound speed, or it becomes transonic. Both the flows are called transonic flows. Transonic means flows that cross the sonic point. Once in D-level nozzle, there was no gravity, but the sonic point was created because of the variable cross section. Here, the sonic point is created because of gravity. Right. If we have both gravity and variable cross section, it becomes very complicated problem. I have done this in my PhD, a couple of papers for relativistic flows where you have variable cross sections and also gravity. You form multiple sonic points and also you get shocks there. You can, if you want, we can discuss on that, but that's not the part of the course. But here the sonic point is formed because of gravity, and the flows that cross the sonic point, they can escape to infinity. So all the winds that are coming to Earth's surface, they have to be transonic. Okay.
Oh, wait, is the sonic point inside of the orbit of Earth? Because outside then we
outside. Sonic point is outside the star surface in general. However, this is what you will have.
Yeah, how far is it?
That depends on how strong is the gravity. You can put the number, maybe in the exercise you will put this. How far is it? It's pretty simple. What is RC? I wrote it somewhere, right? This is RC. 2 gm over VC square. Yes. RC is gm over. This was the expression. Yes. 2v square. So V is basically C, sound speed. Put the sun's temperature, the surface temperature, and put it, find the sound speed, put it here, mass of the sun, put it here, and you'll find how far it is. Okay? Do it later on. So generally it is outside the star, but why it's necessarily outside the star? It can be inside as well. Mathematical quantity. Suppose your star is here. Okay. Then from the surface, the condition is that the fluid has to be, it is transonic, but the fluid has to be supersonic at the surface. More than supersonic means something which is more than speed of sound.
So all emissions will escape. That will only
no. In this case, all emission will escape.
Because that will only decrease in mass.
No. Accretion will also take place. If the matter is there, depends on the conditions. If the matter is coming inside, when the matter is coming from outside, it is cold from outside. It does not have thermal pressure. So it will keep on accreting, falling. Matter which is on the star, it will be ejected from the surface. The outflows are generated from the star, maybe from the stellar atmosphere, hot stellar atmosphere too. The inflows are generally coming from far away, which is cold, and then falling onto the star. Both things can happen. Many things here, if I'm forgetting something. Okay. Now the question is, so let's say this is this star's radius. 4. But R equal to R star. You have to have V equals to V star. Okay. Only winds which are ejected at V star, that will reach infinity because they can cross the sonic points. What if it ejects with slow speeds? Suppose you can eject from any point. Right? Suppose the point is here. At R surface, the velocity is less than the required speed to, for example, for the stone, if it's less than 11.2 meters per second, it's 11.1 meter per second, it will fall back. Similarly, this matter will also fall back. Is it allowed for the assumption that we took? Right?
And you have only two solutions. That's not one of them.
That's not the reason. The reason is time independence. Something is falling at the same point, same radius. Something is going in, coming inside. It's time dependent solution, not time independent. So for time independent solutions, we are not assuming about the falling back matter. But this one more solution exists. If you take k equals -3 here, that you will see in the solutions, you get these transonic solutions. For other values of k, there's whole family of solutions. This is not the end of the story. Let's draw it again. So we have two solutions. Let's look a little bit of history. This solutions were obtained by Bondi in 1952. 1952. Spherical accretion on stars. Now look at the problem. The Einstein's general theory of relativity equations were derived in 1916 and they were solved in 1990, 3 years after that. The equations are very complicated if somebody has studied in general relativity. Okay. Not only non-linear system, but still the solution was obtained in 3 years. But this equation was derived hundreds of years before. The first solution for the stars was given in 1952, much later. Mostly because it's a sonic point problem. It was solved for the cases, other cases later on in the laboratory, not for the stars cases, the winds. So aerodynamic problems sometimes happen to be, they take much longer to solve. So it was, first solution was obtained by Bondi in 1952. And then this solution was used by this one. This was by Bondi. Okay? This is Bondi. And this solution is by Parker, 1958. It was solar winds. By that time, nobody thought why sun will emit wind. Because basic notion is, does Earth emit anything? Do stones go out directly? No. Things don't just kind of go. So physical intuition says that matter should always fall into gravity, cannot be emitted. And by that time, 1958, we did not even have direct, I don't know if they had, but it was not a direct notion that stars can inject matter outside arbitrarily. Doesn't in general. So when the Parker, this is the story which I could not verify on the internet. I tried to find it, but it is that when he proposed this solution to the supervisor said that my name cannot be in this paper. Again, I heard this from my supervisor, so I trust him. So his name was not in the paper. And Parker finished his PhD thesis probably without any paper. You can check. But this was a seminal paper by Parker. He said the sun can emit winds too. Put the numbers of that you can do an assignment and you can do anywhere. You can find out what is the speed of winds at infinity. And satellites can measure the speed. It was found that whatever the speed was projected by Parker, same solution. This is Parker's solution. You can find in the original paper. Whatever speed was projected at r equals infinity, I don't remember the number exactly, but 900 kilometers per second or meter per second, you can check it. Whatever speed is predicted at r equals infinity, the same speed, roughly the same order of speed was observed as well. So this simplified model accurately predicts the solar winds, even with the crude assumption of isothermal system, which is not correct, but still it predicts the same speeds. Now, if you remember the probe which goes on sun, the satellites go. One of the satellites has been named as Parker. This was that much important paper. It was not that much considered by people at that time, just because matter cannot be ejected, so it has to be accreted as well. Even Bondi did not mention about the outflow papers in his paper. It was for accretion. Parker recognized there's one more solution. It represents the winds. And he was bold enough to publish that. Sometimes you have to publish things which are physically not perceptible. Mathematics can say, okay, so now we are not done. This is the story of the two transonic solutions. What about different values of K? Or in other words, different initial conditions. All different values of K will give you all the solutions everywhere. There are some solutions, you will find some solutions which are breeze solutions. These are called breeze solutions. So basically, these winds also escape to infinity, but at infinity they don't have any speed. These are subsonic winds. These are transonic winds, subsonic solutions, both for accretion and outflows. It's true for both. They are subsonic flows, and it's for different values of K, you will find different solutions. You can solve this numerically. I think you can solve this in the assignment if I give. You can right away see it. When you solve it, you will see it right away. It's better physical intuition. These are breeze solutions. For different, if you inject more than the speed which is required for transonic, then what will happen? Nature chooses transonic flows. Okay, one more thing. If you take adiabatic systems rather than isothermal systems, you will see that all these solutions will have different entropy. Adiabatic system has a constant entropy. Constant entropy for one solution. Every solution has one entropy. All the solutions are different in entropies. We assumed isothermal, that doesn't mean the family of solutions belong to only the isothermal case. You can take general equation of state, you will still find the same family of solutions. Each solution has different entropy, but the maximum entropy belongs to the transonic solutions. This is why nature chooses transonic flows. Okay? Entropy always increases. Second of thermodynamics. So in fluid dynamics, it has different beautiful insight, which is nature chooses transonic solutions, accretion and outflows. There are many insights here. Whatever I can remember, I can tell you. What if you eject? So this has maximum entropy. These are smaller entropy. What if you eject the matter from here? Higher speed, right? Problem is, here mathematically you will get this kind of solution. These solutions are unphysical. Why?
Speed from nothing. I mean, no energy conserved.
No, energy is strictly conserved. Energy is conserved, the temperature is constant. No rules is.
I mean, the radius gets smaller, but the velocity gets bigger.
Can get bigger. Radius gets smaller. What do you mean radius? So sun has fixed radius, distance.
Yeah.
These are unphysical solutions because these are double valued solutions. There are two values of velocity at 1 hour, which breaks our. So matter cannot be going out to the same place. You cannot have two states.
Oh, so this is where you get conversion.
Conversion.
This is all based on the assumption that it's spherically symmetric. So if you get that this is stable and this is stable, then maybe you get something like this.
Then it will not be ready for anymore. Okay. So something will happen. So it's mathematical solution, but physically it is wrong. Similarly, you will get these types of solutions here as well.
You have
What?
But you can get the particles in this velocity. What will happen?
You can inject. Right? Okay, that's a good question. What if you inject physically at this point? What will happen? Okay. So if I simulate this, if I do simulations and inject the speed in the particles at this for the fluid higher speed, what happens to that? System gets time independence. First of all, it's not time independent anymore. There's ddt term in the Euler equation. because nature does not care about your assumptions. Right? We assume that system is time independent, but it is. So what happens is, if you inject the matter at this speed, it automatically takes the maximum entropy speed at later on, dissipating some energy. Takes this and it will be transonic. So it doesn't matter. It takes one of the solutions, transonic solutions. I check this. When you inject, cannot continue. This is not physical. The matter cannot go like that. It jumps onto the nearest transonic solution. Once it jumps, then it follows the solution. While it is jumping, it does not break the physics. It only that the system is not time independent in that process. Okay. All right. It's a good question. So this is set of unphysical solutions. Similarly, you get unphysical solutions here as well. Okay. I should have used different pen, but I think you understand. There's one more blank region at the top. What if you inject the solution at here? From symmetry, you can see it might be going like this. This is fourth class of solutions. These are supersonic solutions.
Thanks. Catalytic solutions?
Huh? Catalytic?
No, sorry. You're talking about this, right?
I'm talking about this.
So it's entirely supersonic, and
It's entirely supersonic.
impacts or leaves the star supersonic.
It remains supersonic throughout. Now it's better. Okay. But these are not unphysical solutions. These are also physical solutions. You inject the matter with supersonic speeds. Why does it slow down? Here the matter is just accelerating, right? When you inject the matter with small speeds, it accelerates. When you inject the matter with high speeds, it decelerates. It's the interplay of thermal pressure and gravity. You can check this when you solve the equations. It slows down, but it always remains supersonic. It cannot cross this. It cannot cross any of the other favorable solutions for the assumptions we are working with. It remains supersonic. But these solutions are not very important from physical perspective because generally sun does not emit. It can. If there is a sudden burst, if you look at the images, I suggest you to look at the images of sun. Videos are there. That is burst of matter, and again it falls back. The burst is very strong with supersonic speed. Physically, you can get these kind of solutions, but the most useful solutions are the transonic ones. All right. So that's it. In general, when you do not assume the isothermal flow, each solution has different entropy, separated by entropy. The transonic solutions have maximum entropy, and I told you that transonic solutions basically are similar to the escape condition for solid objects, right? Escape velocity, transonic velocity. That's it. Okay. When the accretion takes place, spherical accretion, is it very reliable? It can always be fine. Assume a mass, random scattered mass, star in between. Mass can have its initial speed, right, in some other direction. Star is here. Initially, matter is moving in that direction. Radial assumption is broken. What will happen in that case? It will have some angular momentum. What I mean is, now we are going to the more general case. Here we assume radially falling matter. How does the matter know that I have to go exactly like that? It can be going somewhere else as well. Is time over?
Yeah.
2 minutes. If the matter is falling like this, it's radial. But if the matter initially had some angular momentum, it will go in, it may not fall radially. In that case, in next class we will study that matter with net angular momentum, it forms a disk. It's not ball like spherically accreted or twins. It forms a disk around stars or black holes. There are beautiful images taken by radio telescopes or ALMA. You should go and check. The disks around the stars are visible. All the stars that you could resolve, young stars, not like Sun. Sun does not have a disk because all the matter is already gone. Only planets are remaining. But in young stars which are still growing, you can see beautiful disks around that. And black holes also have generally disks around there because of net angular momentum. So next class we'll make it a bit more complicated and we'll split the matter around black holes, especially black holes, also stars, which inform disk. Yeah. That's it. Any question?
זה כאילו סודר במחפה. כן, אני יודע, אבל עכשיו זה לא הגיוני. אבל יש לי אבל אין לי כבר את הקצב שאני מבין לפי
לא יודע לאן.
Give exam, right? Today's attendance is exam.
So no attendance today because we had the test.
I had attendance because you gave me the sheets. Yes.
The boundary condition of VLC just gives us k equal to -3, right? That specifies. Okay, so then you said that if we have a solution, which is another k, because of this solution. But he told me that if it's not time invariant with breaks or something.
Even it does not physically look
When you said something about putting something here which won't have enough speed.
the solution will be starting with small speed. Nothing is time. Last, you are talking about the last part of the lecture? And here are the questions.
No.
What did I get?
I don't remember.
Let's simulate. If you eject the matter from here, happens in realistic cases, sometimes it jumps to Sonic point. But it's time if you eject from here, it gives you breeze solutions, which means the matter is getting accelerated, but it's not accelerated enough that it can successfully escape it.
Different case time independent. Different case don't break our assumption of time independent.
No, it doesn't. Everything is time independent.
So the boundary condition only gives us the specific solution.
Different K only gives you non-transonic solutions. Subsonic solutions, supersonic solutions, endogenic solutions.
Yeah.
K equals -3 will give you transonic solutions.
Those are the only ones in this case.
Those are the physically most important ones.
Yeah. Only ones that can escape.
All the winds that come from sun, they are transonic waves. But you can have these as well. Like, at infinity there is no speed.
That's something about the only numerical problem is that to be equal to C, we have this. But if we have others to look at other solutions, we don't have this. But he's not.
In analytical case, you will not have this problem. This problem comes when you cannot solve analytically. and you have to solve numerically. So numerically, you need the gradient at each and every point. Have you ever solved the numerical integration of any equation? When you solve it, you know it. But you have to find, give condition here, then you get the next points. You have the slope, you get the slope.
Newton, I don't remember.
Newton-Raphson.
Yeah.
Many methods are there. So you get the slope, keep on adding, but here you don't have the slope.
Yeah, but if I pick this slope, you don't have any problem.
No, you get the same solution. No problem.
Got it.
Yeah, I'm saying that the only problem numerically is for the case
Answer that.
k equals to 1.
And it's important because this is the most important solution.
Yeah, of course.
Yes, this 0 by 0 form comes from only the two solutions.
So why can't you
start
start from the slope?
Yes,
Say
I
that,
always start
זה
with
אזור מבודד.
and then you set
integrate it outward, inward, you get one solution. Change the velocity slope, so you get basically two solutions. If you solve this,
כן.
you get
צריך לעשות את זה.
you'll get an algebraic equation. You can try to solve this, okay? Because when you solve this derivative, you'll get two solutions equals a square. Two solutions, one positive DVDR, one negative. Positive DVDR,
to this.
you give the initial condition here, put the positive one, you get this solution.
כל הרעיון שאתה
Negative
צריך
one, you get
לכתוב
this
את זה.
solution.
עם הזה שלהם מהפסולים.
נכון, זה כוכבית גדולה.
You didn't create
ראית את המשהו שבני לפסיר על ההצעה?
כן, הוא אמר לך מספיק.
I did not,
איפה רואים את זה?
I never did this.
check.
לא, אי אפשר.
Just the PDF file.
Okay, I will check it.
העברתי,
I sent an
פגשתי
email.
אותו במעלית, ואז הוא אמר לי איפה זה שלכם, אמרתי יש רק שכחתי את זה, ואז הוא אמר לי עכשיו תעלה את זה לזה, והעליתי.
I did not get it.
לא,
This
וואלה,
one goes into the
למה הוא מספיק טוב? מה הוא אמר?
Why did you make it?
זה לא מספיק.
because it's some number plus QQ.com. That's common in China, but it's not very
Let's see
common.
what's your email ID. Number QQ. It's your email ID or it's attachment? Is your email ID, does it have some number?
Yeah, it's just the 10 digits of numbers and at QQ.com.
Change the email ID.
But you can check.
Whose phone is that?
Is it? Yeah.
אין אחי, אני לא רואה את זה.
And I'm using figures. So maybe there's a chance to new summary.
This one, of course. It's really important. There's no assignment, there's no notes to this. Is there?
What? No, not yet. No. Oh, you reminded me. I had to ask you a question. Bye bye.
Upload this. Yes.
I think I got the visualization working. I'll try to.
Okay, what am I saying?
This is the differential equation we have here, dv over dt, and it's translated to dv over dt and d over dt. That looks like how you move in the phase.
T.
Yeah, because you want to say like the velocity, you want to say the how. Okay, so dr dt is just v, and dv dt is just dv dr times dr dt. So
Yes, but when you assume there's no time dependence, everything is time dependent.
no, but you're looking at any single particle, and you're looking at the trajectory it will have in the phase space.
How is it?
But
What is zero here?
this is radius 0.
What is v plus and minus? What is physical meaning?
That's what actually that's what I wanted to ask you, because what does it mean that v is plus when it's increasing and it's decreasing?
When v is minus, yeah, then you can put the boundary condition at the infinity, you get the same solution.
But v should be signed, right? Because you have velocity increasing or decreasing, like the change of rate of radius. Is it coming towards or away from the start?
When you solve the equation, if you give velocity v at r equals to, let's say, infinity,
Yeah.
choose that. I suggest you to do one thing. Solve that dvdr condition, sonic point condition. Choose the initial boundary condition at the sonic point.
Yeah, but it's something else. I don't understand how this curve that supposedly goes into the star doesn't represent matter coming out of the star, because if v V is very high and positive.
Mathematically it does, but physically it doesn't make sense.
Okay, so I just said that you like mirrored it. So
Yes.
So that's what I tried doing here. So we have a phase. Wait, so let's show the not only phase. This is just like calculating the dr over dv over dr and then getting what you move in, how you move in space. Okay. The slope of each vector is dv over dr, and then the size depends on.
Let's look at the positive resolutions first.
Yeah, maybe I'll put it back into
It should be completely symmetric.
What's that?
Yes. Everything in V is squared. It's V squared. Every time V is shared, V is squared.
The solution is square, so it does not matter.
So it doesn't matter if it's plus or minus.
That's what I'm saying. Choose the sonic point. So
No, but you have v times 1 minus c squared over v squared.
no v square.
Yeah, but after you integrate, it doesn't matter. V is always squared.
Okay, yeah, it will be ln of absolute value. So I think you can see the Fourier transform. I don't know. I think there's something weird with the sign because it's slipping out my hand.
Be careful what values you put for the parameters, mass,
So I want to just see if it's free.
When you put the physical point like the mass of the sun.
Yeah, this is. Yes, good. You showed where the physical point would be. It would be gm over 2c squared. I can get it. Okay, not actually.
Just number 4.
What is the question number 4?
And 4 question number 4.
Oh, that's just how
What is the another derived condition of wanted us to develop, we developed something in class considering crowds. So now because you had to mention about the supersonic flow, we have to put some pressure which you did not show us, like critical value of pressure.
Yeah, if you do not put that condition, you get the three solutions.
So that's not what you want us to show. You want us to show what we showed in class.
What did I say? Did I say something? I forgot to show it after that. In the class, what did I say? You asking about the question, or I said something in the class?
Yeah.
Last lecture.
Get two equations related. This one.
Yes.
And you told us that such as dx over the mouse will go in less 4.